Good afternoon, everyone, and welcome to this afternoon's webinar, Hot Weather Concreting, presented by Steve Moore, a senior engineer at Atlantic Testing Laboratories.
Thanks, Howard. So as he mentioned, today we'll be talking about hot weather concrete. As I look out my window here, the sky's blue, the sun's shining, and it's definitely a timely presentation. Hot weather's coming, and all those all the issues that come along with it. We'll outline here. We'll talk about 5 essentials of quality concrete, or what I feel are 5 essentials for quality concrete. We'll talk about how ACI defines hot weather, specifically ACI 305-20. 305 did change a little bit in 2020. We'll talk about some of the problems that we can see in hot weather, some of the mitigation procedures, and we'll talk about some considerations during and after placement. And I've got a slide at the end that talks a little bit about the specifications, the hot weather specifications that ACI has, and that's ACI document 305.1. So here's a slide. It's you know, the bread of the construction industry, concrete, the bread of the construction industry. I didn't coin this phrase, but I like it. You know, if you think about what a bread is, you know, it's kind of a dietary staple, and concrete's kind of the same. You know, most construction projects have got concrete on it, you know, somewhere. You know, as bread, there's not a whole lot of ingredients to bread. You know, water, flour, you know, some yeast or leavening agent or something like that. But not a lot of ingredients, but it's got to be mixed properly, prepared properly. Temperatures are important, you know, and if those things aren't right, then, you know, your bread's not going to be very tasty. You know, might have a bad consistency or whatever. Similar with concrete, there's not a whole lot of ingredients. You see them up there on the screen. You know, obviously this is, you know, these are just rough portions by volume. Obviously, air has no weight. You know, 6% air, give or take, 11% Portland cement. Your aggregates, you know, 65, 70%, you know, that can range a little bit. Water about 16%, obviously that can range a little bit. You know, this is an air mix, so it'd be an exterior mix. You know, those ingredients can shift around a little bit. Obviously, internal concrete's not going to have air in it, or it's not going to have entrained air. It usually will still have, you know, maybe 2 or 3% air, but not a whole lot of ingredients in the concrete. It's not rocket science, but there's a lot of stuff going on inside the concrete chemically. You know, temperatures are very important, you know, how it's mixed and everything like that. Concrete is the second most widely used substance in the world, next to water, which has about 16%. Concrete's got about 16% of water in it. So 5 essentials of quality concrete. Again, this is what I think, but they're certainly all important. You got to have suitable materials. As I mentioned, there's a lot of chemistry going on inside the concrete. You got to have the right cement, the right aggregates. You got to make sure that the cement and the aggregates are playing nice. You know, there's some alkali aggregate reaction. You know, the aggregates can react negatively with the cement sometimes. And that can cause a lot of problems. So you want to make sure that you got suitable materials, and even all the way down to the admixtures. You know, some admixtures don't play nicely with each other; they counteract each other, and things like that. So you want to make sure that all the materials going in your concrete are suitable and they're all playing well together. Proportioning it, mixing it, transporting it. You got to have the right mix. You know, we saw the slide before that kind of had some rough percentages. You know, that's going to change a little bit depending on what the purpose of the concrete is being used for. But, you know, again, you want to make sure that everything's proportioned right. Want to make sure that it's mixed properly, that it's well mixed. Transportation is something that people don't think about sometimes. We had a project up in the Adirondack Mountains here in New York a few years back, and there was no concrete plant within about 60, 75 minutes of the project site. So transporting it was a challenge, mainly because of the time. But they had the right mix. They had some what's the word, retarders in the mix. So that kind of helps. So it wasn't hydrating too quickly before it got to the project. Then once it gets there, you got to place it, you got to consolidate it, make sure you got the right equipment placing it, make sure it's consolidated properly, certainly around, like columns that might have some real dense, large reinforcement. You want to make sure it's consolidated really well around there. Maybe it's, water treatment plant tank walls that, have like number 8 bars on, inside face, outside face, lots of congestion down there at the bottom. Maybe you got bars coming out of the footing, tying into the wall. You want to make sure everything's consolidated real well. And then after that, you got to finish it, you got to join it, especially important for flat work. Make sure you get a good finish on there, depending on what type of finish you want. Timing is very important for finishing. We'll talk about that here in a minute. You want to cut the joints, either form them, saw cut them, something like that. Again, timing is pretty important for jointing as well. And after you're done with all that, you can't get up and walk away. You got to make sure that you're curing it properly. Obviously temperature is very important for that, protecting it from moisture loss, which we'll certainly discuss more of that. So how does ACI define hot weather? And believe it or not, there's different ACI documents that define it differently. ACI 305 defines hot weather as high ambient temperatures, high concrete temperatures, low relative humidity, high wind speed, or any combination that's going to impair, or that could impair, the quality of the concrete due to accelerated moisture loss or accelerated rate of cement hydration. So if you think about any one of those items up above, it's either going to make the cement hydrate quicker. Heat is a catalyst for most reactions, so that's going to cause the rate of cement hydration to increase. That's an exothermic reaction. So as the cement hydrates, it kind of creates its own heat. So now you've got heat adding more heat, just kind of, one kind of just adding to the other. So you want to make sure that, you're controlling all those temperatures, and again, moisture loss as well. So some of the problems we can see in hot weather in its fresh plastic state before it starts to set. Obviously, you've got increased slump loss and water demand. As the concrete starts to get stiff, the people placing it, they're going to want to add some more water to it. More water, that's going to increase your water cement ratio, which could, ultimately decrease your strength, your durability. Adding more water is going to increase your chance of plastic shrinkage or hardened shrinkage. The more water that goes into it, the more water that can come out of it, which is really what causes the shrinkage, is that volume loss. You're going to get increased rate of setting. It's going to set a lot quicker on those hot days than those cool days. Obviously, increased plastic shrinkage. Again, that's that volumetric change. The moisture loss, and you can have hard. It can be difficult to control the air content during hot weather. Again, heat is a catalyst, and the admixtures that are added, they react with the cement to create the air in there. So as you start to introduce more heat, that reaction is gonna change, and you're gonna start to have trouble controlling your air content. So here's a chart that I copied from the Portland Cement Association. We can see it's about a 30% decrease in set time for every 10-degree increase in temperature. So that really goes both ways in both cold weather and hot weather. So if we got a project that's maybe placed concrete last week and it was about 60 degrees, the set time, approximate set time is about 8 hours. And maybe next week it's going to be 80 degrees on the same project, and probably the same crew of people working on the job. That set time is pretty much going to get cut in half. So we want to make sure that everybody is aware of that. Most of the flat work guys that are doing the finishing, they understand that, but it's certainly something that that everybody should understand and be prepared for. And like I said, it goes both ways. That set time is gonna increase as the temperature gets cooler. So plastic shrinkage cracks, that's probably one of the most common problems that we see, and that occurs when the rate of evaporation exceeds the rate of bleeding. So and it's mostly an issue when you've got flat work, those slabs where you've got a large surface area exposed. Some mixes bleed a little bit more than others. Those mixes with fly ash, slag, silica fume, they don't tend to bleed quite as much. But as the bleed water comes up to the surface, again, if that rate of evaporation exceeds the rate of that bleeding to the surface, that top surface is going to dry out, and you could potentially get some shrinkage cracks. They're typically pretty shallow, but sometimes they can be pretty deep depending on how much that surface is drying out, how much the concrete itself is drying out. Maybe more than half of the thickness of your slab section. They're typically parallel, kind of sub-parallel oriented. Spacing can be anywhere from 1 to 3 feet. Maybe they're not always parallel, sub-parallel oriented. Sometimes you can kind of see a bit of a map crack pattern due to drying shrinkage. But typically we'll see those parallel, sub-parallel cracks. And obviously it could decrease your durability. Think about bridge decks and sidewalks that got de-icing salts being sprinkled on them, and those chlorides are going to get down into the reinforcement layer and potentially increase your corrosion rate or start to cause corrosion. So this might be hard to see for some people, but here's that parallel, sub-parallel orientation. The long dimension of this placement is kind of in the left, right, east, west direction, and you're getting those cracks that are that are in the opposite direction of the long dimension. Here's a core that was taken out of a roadway. When I was putting this presentation together years ago, Texas DOT had a lot of information on their website, and they did a lot of research. Obviously they've got high temperatures. It's a real dry environment. So low humidity. So they deal with hot weather issues all the time down there. So this was a core that was taken out of a plastic shrinkage crack, and you can see it's pretty much halfway through, maybe more than halfway through this core section here. Looks like probably a 12-inch thick concrete, some pretty large aggregate. And down here at the bottom, it's kind of weird to see asphalt at the bottom. A lot of times, or at least here in New York, we'll see an asphalt overlay on concrete. We won't see the asphalt down here at the bottom. But in Texas, a lot of times what they'll do is they'll use the asphalt to stabilize the roadways sometimes, and then they'll place the concrete over it. It's pretty obvious to, we don't see any reinforcement in this core, but It's pretty obvious if something like this were to be in the northeast or northern states, you start to put some de-icing salts in there, it's going to migrate down through there relatively quickly. So that's obviously going to impact your durability. So problems in the hardened state, increased tendency for drying shrinkage, which is a little bit different than plastic shrinkage. Still, kind of the same cause though. You've got moisture leaving the surface, some amount of volume leaving the concrete, causing the concrete to shrink a little bit. They show up in different places than the plastic shrinkage cracks, but they have the same effect. There can be some variability in surface appearance, color variations, or maybe cold joints can develop. If you've got colored concrete that's placed in different temperatures, that can really change the color of the concrete. Eventually it kind of stabilizes so it all looks the same, but maybe for 6 months or a year, you might have different colored concrete because of the higher temperatures. Same thing here with the hardened state, decreased durability from cracking, increased permeability, and potential for corrosion of the reinforcing steel. So no different there. Something else to keep in mind: decreased 28-day compressive strength at higher temperatures. We get what's called the crossover effect, and that's what's shown in the figure here to the right. And here we're relating strength to maturity, and the maturity is just a product of time and temperature. So if we were to keep time or age constant, we see these higher temperatures, you're going to get higher strengths with the higher temperatures, but eventually you get to this crossover point where those higher temperatures are going to be detrimental to the long-term, the later ages of concrete. So typically we see decreased 28-day strengths with higher temperatures. That crossover effect, it's going to be different for every mix. It's going to be at a different maturity index for every mix, but it's there. It's going to be there pretty much for every mix. So we know we've got hot weather. We don't stop concrete placements in June, July, August. Texas has got hot weather, obviously. They deal with it a lot more than we do. So what can we do to mitigate it? Cooling the concrete. If we can cool down the concrete as much as possible prior to placement, that's we're going to be ahead of the game. We want to have proper consistency for rapid placement, effective consolidation. We want to make sure we can get it in there and get it consolidated. Those warm days where the concrete starts to stiffen up and we lose slump, that's when we want to pay attention to the mix. Maybe put some admixtures, some plasticizers in the mix, especially for maybe those column placements that have really large congested reinforcements. Those tall, the tall 18-20 foot tank walls on water treatment plants that have got large bar. We want to make sure that we've got the proper consistency so we can place it and consolidate it properly. Minimizing that transport time, minimizing placement time, minimizing finish time. Just make sure that everything is planned out really well. You got the right mix, you got the right people, you got the right equipment, and you plan for it. At 2 o'clock in the afternoon, concrete placement when it's 95 degrees out, when people are scrambling around, at 1 o'clock or 1:30 to get everything ready, that's just a recipe for disaster. You want to make sure that you're planning properly, especially for those large flat work placements, where you've got the large surface area that's exposed, and you've got a greater chance for that shrinkage. So controlling concrete temperatures during production, I mentioned cooling the concrete as much as we can as it's mixed will kind of put us ahead of the game. Protect the ingredients from sunlight, cover stockpiles. That's probably one of the most common things that a lot of producers do. They'll have them under cover, and they'll pull them out as they need them to put them in the hopper. Cooling the ingredients. You can spray the stockpiles down with water. Obviously making sure you're getting accurate moisture contents for your mix. It's really not practical to cool the cement, although maybe you can cover the silos or something like that, but we don't see that very often. Cooling the aggregates, the coarse aggregates, the fine aggregates. Remember, those are 65, 70, 75% of the mix by volume is the aggregate. So if we can cool those aggregates down, that's really going to help us out quite a bit. We can cool the mix by using water. Maybe it's well water that's coming out at 50 some odd degrees or 60 degrees. That's certainly going to help. You can cool the mix using ice, maybe chipped ice or flaked ice or something like that. I've got a dollar sign next to that. Obviously, there's some cost to that. Down south, they use nitrogen. They'll take a nitrogen. They'll take a lance and put that lance into the discharge of the concrete truck, and they'll spray some nitrogen, nitrogen gas in there, and they'll cool it down that way. We don't see that too much in our area up here in the Northeast because that's pretty expensive. But again, cooling the aggregates, that's going to have the greatest effect. It's probably going to be the most economical. And cooling your aggregates by about 2 degrees, dropping it by 2 degrees, that's going to drop your overall concrete temperature by about 1 degree. So cooling those aggregates is definitely going to have the greatest effect. In the appendix of ACI 305, there's a formula that will predict the concrete mix temperature. And we see here we got two formulas. One is without ice here at the top and with ice here at the bottom. We've got this coefficient, and then you've got the temperature of the aggregate, the weight of the aggregate, the temperature of the cement, the weight of the cement, temperature of the water, weight of the water, temperature of the aggregate, and the weight of the water in the aggregate. So that's your moisture content right down there. And then this next formula, here's where the ice comes into play. You've got your weight of ice here and your weight of ice here. So, making your numerator smaller, your denominator bigger, that's going to drive your quotient down. One thing to remember is you're adding ice. This weight of the ice, you need to account for that in your mix because that's water, right? So you need to subtract whatever, if you're adding, 50 pounds of ice per cubic yard, you got to subtract 50 pounds of water per cubic yard. I've talked to a couple of people that have used this formula, and mainly both of them actually. Mainly the bottom formula, they had an ice plant. And they said they did this calculation every morning, and it was accurate within 2 degrees. So that's pretty impressive. So some considerations during placement. I mentioned before, I'll mention it again: planning, preparation, make sure you got the right equipment, maybe have some redundant equipment. If maybe you want to have two concrete vibrators just in case one goes down. You want to consider maybe having some redundant equipment, extra equipment. Make sure you got the right people. The people know what they're doing. They know what the temperatures are going to be. Plan for the weather again. If it's going to be hot, make sure you got plenty of water on hand. Maybe consider large placements early in the day. It's not unusual for us to be on concrete pours, large 300, 400, 500 yard concrete pour at 5 o'clock in the morning, in July or August. you know, to just account for, you know, the heat of the day. Consider the project schedule, you know, if you can move some of those, you know, some of that flat work around, if you can, you know, shift it around in your schedule. Sometimes you can, sometimes you can't, you know, maybe consider that. You know, if you got a slab that you can push off until, you know, October or something like that, you know, rather than placing it in August, maybe that's not a bad thing to consider. And what you're placing obviously makes a difference too. You know, the flat work is really what, you know, where the shrinkage and that moisture loss and, you know, again, just that large surface area being exposed. So just some things to consider. You know, after it's placed, you know, got to protect it from moisture loss. You got to keep that water in there, and you got to let that water hydrate with the cement. You know, protected from high temperatures, direct sunlight, low humidity, high winds, things like that. All those things that ACI defines as hot weather. Exposed surfaces, you want to keep them from drying for 7 days. Moist or membrane curing, I prefer the moist curing over the membrane curing, but either are allowed. And that's 7 days. That's an ACI recommendation in 305. Your project requirements might be different, and it might change depending on what the temperature is. There may be different curing requirements. You know, when the temperature gets above 85 or 90 degrees, then, you know, when the temperature is 60 or 65 degrees. Form surfaces, sometimes you maybe want to loosen those so you can put some curing water on them. You know, again, ACI 305 kind of mentions that and recommends it. You know, maybe you got some, you know, maybe, you know, again, thinking of those tall, you know, 18, 24-inch thick walls on a water treatment plant. You know, there's a lot of concrete in there. You know, maybe you want to get some water down in that. You know, crack the forms open after a couple of days and get some water in there if you can. The other thing, and this pertains to both hot weather and cold weather, you want to avoid rapid heat loss or heat gain. And ACI defines that, in whether it's hot weather or cold weather, 5 degrees in 1 hour or 50 degrees in 24 hours. And think of concrete as kind of like a ceramic material. That really doesn't like thermal shock, and you start to get temperature changes above 50 degrees in a 24-hour period. You know, you're starting to introduce some thermal shock into the concrete, and then you can get cracks at corners and things like that. So whether it's hot weather or cold weather, you want to avoid rapid heat loss or rapid heat gain. So this is a picture I took, it's probably been 10 or 12 years ago now. This is a new bridge deck over in Vermont. You can see they've got some of the placements kind of placed in hopscotch, covered with white poly. You can't see it, but there's burlap underneath that white poly. Actually, you can see the burlap right here. They're getting ready for a couple more placements here. They've got some redundant equipment, like I talked about. They've got this pump truck here. They got another one waiting just in case this one breaks down. Kind of hard to see, but this white fire hose right here, that's water. They've got sprinklers, foggers ready to go. So after they place it, you can see them unwrapping some burlap right here, getting ready to go. This is good planning, good preparation. They got plenty of people there. They got all the right equipment. They got some redundant equipment. I don't know if I mentioned it. This picture was taken about 5:30, 6 o'clock in the morning. So they're accounting for the time of the day. Also, this is how it's done, right? So it's a good picture. If your project references ACI 305.1, which are the hot weather specifications from ACI, you want to get familiar with this figure, which is in ACI 305. And this will tell you what the rate of evaporation is per surface area. So it gives you, the evaporation rate in pounds per surface, per square foot per hour. I will say that this formula was developed, I want to say it was by NOAA, maybe it wasn't by NOAA, but it was developed for the rate of evaporation on an open body of water. So if you do not have any bleed water on the surface, it might overestimate the rate of evaporation a little bit. But if you're planning, that'll give you kind of a conservative number to deal with. This chart's not too hard to use. You enter with the you enter with the air temperature right here. You move up to the relative humidity, which in this case is 40%. You move to the right over to the concrete temperature, which in this case is 60 degrees. That's pretty good for concrete. Concrete's pretty comfortable at 60 degrees. And then you move down to the wind speed. Wind speed right here is 25 miles per hour. And then once you get that, you move over here to the left to get your evaporation rate, which is, I don't know, maybe 0.15, pounds per square foot per hour. So this would give you a good idea of what your evaporation might be. And again, this is referenced in 305.1. So this is something, if you're an inspector and 305.1 is referenced, you should probably get familiar with this figure here. Some things to consider when you're doing your tests during hot weather. Obviously, you always want to sample and test in accordance with applicable ASTM standards. Maybe you want to do it more frequently. And again, think of the slump loss that you're getting or that you might be getting. Think of the air content. If you've got an air entrained mix, as the temperature changes, that air content is likely going to change. Maybe you want to be in communication with the batch plant, to change the dosage rate of some of the admixtures, either to account for that slump loss or the change in air content as you get to the warmer part of the day. Obviously, you want to maintain curing temperatures for your strength specimens. Those are those cylinders. You want to keep those nice and comfortable. Want to make sure that those are being cured at the proper temperature, 60 to 80 degrees. Avoid moisture loss in your composite sample. That's a sample that you get in the wheelbarrow when you're sampling it. If it's taking you a while to make your samples, get to your slump and air and cylinders. And again, avoiding moisture loss in those cylinders that you cast. Most people put lids on them and then we'll put them in a cooler. We like to put water in the coolers, especially during the summertime. There's always water available on the concrete trucks, and we'll put water in the coolers, and then we'll set the cylinders down in the coolers, and the water helps to kind of temper the temperature inside the cooler. So it won't heat up as quickly. So that's always a good idea. And obviously it adds a little bit of humidity to the specimens. You're not introducing water into the specimens, but you're helping to keep them from drying out. Inspections, if you're an inspector during hot weather, again, you want to make sure you read and understand all your project specifications. Make sure you understand what's referenced. If 305.1 is referenced in the specifications, you want to get familiar with that chart that I showed. Understand what there may be different requirements based on the temperature. It seems like 85, 90 degrees is somewhere in there is usually where there might be some different things to consider. Either the frequency of testing or documenting temperatures or whatever. Frequently document the air temperature, concrete temperature, the humidity, those ambient conditions, wind, evaporation rate from that chart, things like that. Write down all the test results, obviously. Placement procedures, curing procedures, take pictures, that picture that I showed of the bridge deck. Pictures are worth 1,000 words, everybody says it. And they're good to put in the project file, make part of the project records. And the last bullet there, whatever notes, it's great to write all of this stuff down. But if your inspector takes his field book and goes to the next job and doesn't make a copy of those field notes, and they don't get made part of the project documents, those notes are good to the inspector that has them in his back pocket, and that's it. So make sure all those notes. It's really easy for those notes not to be made part of the project record, because everybody, myself included, I say everybody, most people, they walk around, with those field books. Again, make sure that information is getting made part of the project document. So if there are any issues down the road, we can take a look at some of that documentation, have a better understanding of what was happening that day. I mentioned specifications for hot weather concreting. That's ACI document 305.1. This came out in 2006. It was reapproved. I believe it was reapproved in 2020. And if I didn't mention it, 305 changed a little bit in 2020. There weren't a whole lot of significant changes, but there were some changes, and the document got reorganized a little bit. So some of the section numbers don't are a little bit different. So if anyone's specifying that document in any of their specifications, just maybe take a look at that and make sure you're not referencing a spec section or a section that isn't appropriate or deals with something else. But anyway, 305.1, a lot of times they're incorporated just by reference into the project specifications. Always use them in their entirety. Don't cut and paste, because there's some things that could easily be taken out of context. If you're just kind of cutting and pasting and using bits and pieces. It's very easy. It's very easy to understand. It's kind of written in the typical 3-part CSI Construction Specification Institute. Where it's got part 1, part 2, part 3. So it's pretty easy for everyone to understand. So it's pretty easy to incorporate into the specifications just by referencing it. So. Okay, we're going to move on to some evaluation questions. And the first question here, question 1, how does ACI 305 define hot weather, high ambient temperatures, high concrete temperatures, low relative humidity, high wind speed, or all of the above?
Steve, we do have one question.
Okay.
What are your thoughts on sealing concrete?
There's different types of sealers out there. Depends on what type of sealer. I mentioned curing compounds or curing membranes. ACI does, I believe ACI considers some of the curing compounds to be membranes, and I assume that's because they probably act as a sealer or a membrane on the concrete. Personally, I like the wet cure method, and even better, you can wet cure and then put poly on it. You kind of get the best of both worlds there. But those are my thoughts. ACI does allow for it, and again, I think they consider some of those as membranes. But just look at whatever the product is and make sure you're using the right product for the right application. And it's not there's different types of sealers out there, xylene sealers and stuff like that are used for different purposes. So just make sure it's the right product for the right application.
If you'd like to continue with the answer.
Okay, yep, that should be an easy one. All of the above. Most people by now know if all the above is an option, it's probably the right option. Question 2, true or false, hot weather and high curing temperatures can cause lower 7-day strength and higher 28-day strength. True or false? And I'll take any other questions, Howard, as they come in.
This one is short. It says admixtures used. So I'm not certain of what they're looking for.
I don't know of any admixtures that can be used in place of a curing compound or a curing membrane, so I'm not sure if that's where that question was headed or not. I'm not familiar with all the admixtures out there. There's a whole bunch of them, but I'm not familiar with one that would serve as a curing compound. So that answer is false. You do not get higher 28-day strengths with higher temperatures. Question 3, true or false, air content is easier to control in hot weather. So with these webinars, I've been doing these for quite a few months now. It's easy to reach out geographically to a lot of different places. I'm always curious to know where everybody's from. So if everybody has a minute, if you don't mind, maybe put in where you're at, maybe city, state, or something like that, just so I can get an idea of where everyone's at. Probably got a lot of people from New York State, but we've had people from Alaska and Virginia and other places too. So just curious if anybody's willing to share that information. That'd be nice. So the answer, obviously false. Air content can be very difficult to control during hot weather, which is why sometimes maybe you want to start testing that air, maybe you want to test the air content a little bit more frequently, and your project specifications may call for that. Question 4, cooling which of the following during concrete production has the greatest effect in cooling freshly mixed concrete? Cooling the water, cooling the aggregates, cooling the cement, or cooling the admixtures?
Steve, another question. Do you recommend having a high-low temp? Excuse me, let's try that again. Do you recommend having a high-low thermometer in the curing box to ensure the temperature did not get too high during the curing process?
Yeah, absolutely, absolutely, and that can really help to troubleshoot some problems. I mentioned higher 7-day strengths, with higher temperatures, lower 28-day strengths with higher temperatures. So when we test those cylinders, if we can see that they were exposed to higher temperatures, it might help us to troubleshoot some problems. If we're getting low 28-day strengths. But a lot of times, July, August, we see, maybe it's a 4,000 PSI mix that's, got, 3,500 at 7 days, and everybody thinks, wow, great, 7 days, we got 35, we're going to reach 4,000, no problem. And then the 28-day breaks come back at, 3,800 or something like that, or maybe they stalled out. That can really help us to troubleshoot what might be causing that. So that's a good question. Answer to question number 4, what has the greatest effect, cooling what, which ingredient? Obviously it's the aggregates. Again, it's, that they take up 65, 75% of the concrete by volume. And our last question here, ACI 305 recommends that concrete curing procedures continue for at least how many days? 1 day, 3 days, 7 days, or 14 days? Again, that's ACI. Those are ACI 305 recommendations.
Steve, one more question. Any thoughts on shrinkage reducing admixtures?
Yes, they're very effective. I do have some experience with those, doing some mixed designs using those. And if you've got a project where your shrinkage tolerance is really low, they can be very valuable. I would recommend, if you've got a project that specifies shrinkage be, below a certain level, probably not a bad idea to do some laboratory trial batches and some shrinkage testing, just to make sure that your mix is going to meet those requirements. And then just because your mix meets the requirements in the lab, again, you really want to make sure that you're curing properly in the field, because if you're losing water from your placement in the field, that's volume that you're losing, and you're going to get some shrinkage. But shrinkage reducing admixtures can be very, very effective. They're also a little pricey, but repairing shrinkage cracks is not cheap either. So answer number 5, 7 days. That's what ACI recommends for curing, and that's moist curing for 7 days. Your project specifications may be different, and it may be different based on ambient temperatures. I think New York State DOT, I think their bridge decks, I think they require 14 days of moist curing. And I think if the temperature drops below, a certain degree, maybe 40 degrees, during that 14-day period, you need to add another day of curing onto that. So something to keep in mind. So I don't know if there's any more questions left, Howard, but I'll certainly take any more questions. My contact information is there. If anybody has any questions, certainly willing to share the PDF presentation to anybody if they want it. Our website, atlantictesting.com. I encourage you to go to our website. We do a lot more than just testing. Of course, we do the standard, soil and concrete testing, but we got a bunch of other services that we could provide. So go to our website and check it out. Here you can see that picture of that bridge deck blown up a little bit more. You kind of see what's going on a little bit better.
Steve, another item, any insight into the effects of other substitute materials, and fly ash is called out specifically, on the situation during hot weather?
Fly ash has got a lower heat of hydration, so replacing some of the cement with fly ash can definitely bring down your overall concrete temperatures. My experience, you got to be in that 25% or higher range. Lower percentages of fly ash can help mitigate some other things like ASR and stuff like that. But if you're looking to control heat of hydration, anything less than 25%, I don't think is going to give you a lot of bang for your buck. I've seen some fly ash replacements up to 50%. If you do have a high fly ash replacement percentage, like 50%, just be prepared to not see full strength at 28 days, because that fly ash and some of those other supplementary cement materials tend to gain strength later in age. This particular project, where I said we had 50% fly ash, they didn't have a 28-day strength requirement. They had a 56-day strength requirement because that fly ash gained strength later on. But those supplementary cementitious materials can certainly help, especially those mass concrete placements, like if you've got a dam or maybe a wind turbine foundation or something like that, adding some fly ash in there can certainly help. Although nowadays fly ash isn't as plentiful as it used to be. Any other questions?
There are not at this point.
Okay. Well, like I said, my contact information is there. If anybody does have any questions, I'd be happy to answer them. Other than that, I think I'm done.